Let's talk the other half of electromagnetism, which is, of course, the magnetism bit. Now, normally there's two types of magnets that we're going to be interested in. There's going to be the classic bar magnet, or the permanent magnet, which is usually a magnetic material like iron or such, or neodymium, or which has a permanent magnetic field placed upon it and becomes magnetized, or the other type is electromagnet, which is basically a coil of wire, because a moving charge causes magnetism, causes magnetic field. Okay, so at the moment, magnets always have, or magnetic dipoles always have a north and south. If you were to cut that in half, then you get two little magnets, north and south. If you cut those in half, you'll get two even smaller magnets with a north and south. And at the moment, we cannot separate those poles. Theoretically, it is possible to have a north pole or a south pole by itself, but that has never actually been observed. And just remember with magnets, while these act a bit like electrostatic forces, these are not positive and negative. These are north and south. We do not call north positive. It is north, south. And this way we can tell whether we're dealing with magnetic fields or electric fields. And just like before, like fields, like poles, repel. So if I have two magnets and they've put the north poles together, then they will repel, they will push away. Unlike poles, attract. So if you have a magnet north, a magnet south-north, and they will actually pull together, and in the end they'll actually act as one big magnet with the north pole here and the south pole over there. Now, there's three types of materials. We basically say materials can be ferromagnetic, which means that they hold a magnetic field, hold magnetic orientation. So basically these make the magnets. You get non-magnetic, which, as you can probably imagine, they're non-magnetic. You also get paramagnetic, which can become a magnet when exposed to a magnetic field. But we're only going to be really worried about ferromagnetic at the moment. At the moment you turn the magnetic field off with a paramagnetic substance. Maybe you turn it off, just the dipoles in there randomly align and it becomes non-magnetic again. So ferromagnetic ones will become magnets in their own right. So magnetic fields have a unit or unit of Tesla, after probably the world's greatest electrical engineer, Nikola Tesla. These can also be called newtons per amp meter. And the symbol for the magnetic field is going to be a capital B. There are other units for magnetic fields, but this is the standard SI unit, the KGS system. You also occasionally come across Gauss. 1 Tesla equals 10,000 Gauss, just out of interest. Okay, so just like circuits, if you have a north and a south, okay, Okay, let's just talk about size of magnetic fields. Magnetic fields. Now, normally the Earth's magnetic field, Earth has a magnetic field, which allows us to use compasses and things. It's about 50 microtesla. So Earth's magnetic field is tiny, tiny, tiny. If you're talking a strong bar magnet like a neodymium, these are the strongest permanent magnets you can buy easily, strong permanent. They're approximately 0.6 Tesla. They can get up to 0.2. They can actually get up to 1 Tesla at a point. But these are incredibly strong. I mean, the average fridge magnet is maybe 0.01 Tesla. MRIs, if you go up to the hospital and get an MRI, they can be between 1 to 9 Tesla. We have made them up to 200 Tesla. We can actually make much stronger magnetic fields than that, but it usually involves detonating a nuclear weapon, so that's pretty much out of it. So when we draw magnetic field lines, just like magnetic field lines are just pretty much the same as electric field lines. Go from north to south. So if this is the north, this is the south, the field lines will go around in a loop. They'll start at the north, they never cross. The more field lines there are, the stronger it is. Do not cross. The more field lines, the stronger the magnet and the magnetic field. And what these actually represent, well, if you were to stick a compass on one of these lines, the compass would point along that line. So if I put a compass there, point there. If I put the compass there, it'd point there. If I put the compass there, it'd point there. So the compasses usually point towards north, sorry. So the compasses will point along these field lines. And if you actually get some iron filings and a magnet, usually put the magnet under the paper, sprinkle the iron filings on top, you will actually see these lines as the iron filings line up and turn to meet the magnetic field. So magnetic fields, we use them for lots and lots and lots of things. One of the very earliest uses of the magnetic field, of course, was navigation. But we've used them for we use them for magnetic storage. That used to be audio tapes, videotapes. Now it can also be things like the hard drive, the old hard drives on your computer. Magnetic fields you can use for steering electron beams. Magnetic fields do turn up. They're often something you have to be a little aware of, because if you expose a computer memory to a strong magnetic field, you can actually wipe the memory. Okay, so anyway, we'll be doing some more in a second on charged particles and magnetic fields.